Okay, so today's lecture is going to be on continuity. And so what is the exact definition of something that is continuous? So, a function is continuous if the limit as x tends towards a of f of x actually equals f of a. Okay? So, in the discussion in the last class, for a limit to exist, the limit from the left and the limit from the right have to agree. I mean, they have to go to the same point. But just for a limit to exist does not mean that it's actually continuous at that point. Okay, so I gave you all an example in the last class of, let's say, f of x equals 3 if x does not equal 2, and 1 if x equals 2. So what would this thing look like? 1, 2. Okay. Now the limit for this problem exists. Okay? If I approach from the left, it looks like I'm going towards 3. If I approach from the right, yeah, it's going to 3. So the limit itself exists. Okay? So the limit as x tends towards 2 of f of x equals 3. Okay? But f at that point actually equals 1. Okay? So we can say, therefore, f of x is not continuous. At 2. Okay. So for a function to be continuous, it actually has to, I mean, the limit has to exist and it has to actually equal the function value at that point. Now, in this case right here, this is not that big of a deal. So what this is known as is this is known as a removable discontinuity. Okay? So a removable discontinuity let's classify the different types of discontinuities that we can actually find. So we can have a removable So, with a removable discontinuity, the limit from both directions will exist, but we have an infinitely small hole just at that point right there. And so, in later forms of math, you'll figure out that this is called a thing of measure 0. And so, we in general ignore it. It's not that big of a problem when you're talking about modeling things and stuff like that. This is an infinitely small point that just has a hole in it. So when you talk about continuity, if you're tracing your finger along and, oh, I gotta pick my finger up and move it over there, that's a removable discontinuity. not that big of a deal. Okay. A bigger problem is also a problem that I was showing you on last time, which is, say, f of x would equal, say, 3 if x is less than or equal to 2, and 1 if x is greater than 2. Okay, so now a problem like this, 1 and 2, 1, 2, and 3, and so I put a solid dot right there, and I have this guy extending off to that direction right there, and an open dot right there, and have that extending off in the opposite direction. Okay, this type of discontinuity is a jump. All right, now, jump discontinuities are more difficult to deal with. When we talk about modeling in a sense, one of the problems I ran into a couple years ago, I was modeling, the formation of plasma in a lab. But not plasma in the sense of blood plasma, but plasma in the sense of the fourth state of matter. You consider like lightning or aurora borealis. Okay, so we can't form this in a lab, and the easiest way to model it is like an explosion. What happens when you end up with an explosion? You end up with a shock wave, and you have to treat these shock waves in very special cases. So what that does is the shock wave actually gets into a type of jump discontinuity and creates problems with your models. Okay, we have even kind of a worse type of discontinuity. I wouldn't say worse. Yeah, that would be an infinite discontinuity or a singularity. Okay, so when we talk about something like, let's say, f of x, which equals 1 divided by x. Okay? And so, remember that in the last lecture, when we were talking about the entire concept of Newton and Leibniz and the definition of the derivative, what was the main concern that we had when in a relationship with that problem? You can't divide by 0. Okay? So, if I said f of x, which equals 1 divided by x, this is going to approach a singularity. Now, if I approach from the left, this thing would actually extend down towards negative infinity. Okay? Now, if I approached from the right, this thing would actually extend towards positive infinity. So how does this make sense? So let's say I was getting closer and closer towards 0. Okay, so I'm going in this direction right here. So let's say I plugged negative 1 divided by 1,000 into this equation right here. What would it do? It would flip that fraction upside down, and I would get negative 1,000. If I plugged negative 1 divided by 1,000,000,000 into this problem, so I'm getting closer and closer to 0. Well, it flipped that fraction upside down, and I would get negative 1,000,000,000. So this would be approaching negative infinity in this way. And so, if I was going this way, if I plug in 1 divided by 1,000,000,000 into 1 divided by x, I'm going to get 1,000,000,000. Okay, so it's approaching infinity in this way, and it's approaching negative infinity in this way. And so this right here is an infinite discontinuity. continuities, we can describe them. What the different types of singularities that we could actually come into. So in the last class we were talking about limits. We had left-hand limits and right-hand limits. Okay? So if we looked at a different discontinuity, let's say different infinite discontinuity. Let's say f of x would equal 1 divided by x squared. Okay, so now since it's squaring this thing, if we're approaching from the left or approaching from the right, it's going to turn it to positive. So this guy would look like this. So if I'm approaching from the left or I'm approaching from the right, it's going to approach the same limit. So what we say in this case is that the limit well, let's say this. X tends towards a of fx tends towards infinity. My marker is dying. I'm not grabbing another one. If and only if the limit as x tends towards a from the left of f of x tends towards infinity, and the limit as x tends towards a from the right of f of x tends towards infinity. So, if you're approaching from the left and approaching from the right, and both of them are tending towards infinity, well, then you can actually say, yeah, the limit as x tends towards that point of f of x tends towards infinity. Okay. And there's a slight discrepancy between my notes and y'all's book's notes. Because they say the limit as x tends towards a of f of x actually equals infinity. If and only if the limit as x tends towards a equals infinity, and from the left and from the right equals infinity. I do not use that notation. And if you look into the fine detail of most calculus textbooks, they have a little caveat at the bottom of the page that says, it doesn't actually equal infinity. This is just notation, because what is infinity? Infinity is not a number. Infinity is a concept. There are different. There are actually different types of infinity. We refer to them as cardinal numbers. There's countable infinity. There's uncountable infinity. There's a lot of different concepts when it comes to infinity. Like, some people ask the question, what is infinity plus 1? Well, infinity plus 1 is infinity. Well, what's infinity plus infinity? No, it's still infinity. One of the ways to describe infinity was a very old problem that was actually referred to as Hilbert's Hotel. So if you've got a hotel with infinitely many rooms and the hotel is completely booked, and one person shows up and they want a room, let me tell everybody, move over one room. We'll put that guy in that room. If you have an infinite hotel that's already booked and a carriage shows up containing infinitely many people, well, what do you do in that situation? Tell everybody in the hotel to move to the eating rooms, and we'll just put all those infinity people into the opera rooms. So there are different types of infinity. That's why I always use an arrow and I don't write that things just equal infinity. Okay? So one of the better ways to describe continuity I think is actually your graphs. Okay? So, on the test, how is this going to show up? I will put a graph on the test, and I say, state the interval of continuity. Okay, so let's look at a problem, and let's ask, where is this function continuous? Give you all a second to draw it. Okay, and we do have the concept of being continuous from the left or continuous from the right. Now, when you're talking about intervals of continuity, you're going to have brackets inside of the problem. So this point right here is going to get a bracket. So it is continuous from the right. So this would be -8, then we go to -5. Okay, so if I put my finger on this thing, I got to pull my finger up. All the way up to that point right there. So that's going to go from -5 up to 2, and then we'll union that with 2 to 5. And this guy's going to get a parentheses because we have an open dot at this very far end. Okay? So this right here is the interval of continuity. Okay, so when talking about things being continuous, basically the question is, can you put your finger on the line and continuously hold your finger onto that without going over a jump, a hole, or anything like that, okay? And now, when it comes to brackets, brackets will only appear if it's a disjoint set or it occurs in an endpoint, okay? So if I did something like, let's say, okay, so I'm going to call this 2, I'm going to call that 4, I'm going to call that 7, I'm going to call that -1, I'm going to call that, say, -3, and that point right there, let's just go with -6. Okay, so that would be parentheses -6 up until -3, and then union -3 to -1. Now this guy's going to get a bracket, okay? because these two sets are disjoint from each other. And then union, okay, this would be, that gets bracket. 2 to 4, let's union that, 4 to 7. Okay, so this would be the interval continuity. Okay, because you can only talk about something being continuous at an endpoint, not in the middle of this. So why am I not putting a bracket on this -3 right here? This is a jump discontinuity. Okay, well, there's a big jump right there. And if you put a bracket on it, by set notation, it implies, oh, if you put a bracket, it's continuous at that endpoint. Well, no, it's not. But if we talk about this endpoint right here, there's nothing over here at all. So these are disjoint sets. Okay, so we have a set that's right here. We have this break in the middle. And we have another set right here. So that's why I put brackets on the endpoints of this one and this one, because well, it's just disjoint from the other set. But at this point right here, this is in the middle. And so I'm not putting a bracket on this guy because he is in the middle of that set. So when we talk about things being continuous from the left or continuous from the right, it only works with endpoints, nothing in the middle. Okay?